Hello everyone, welcome to my channel. So this is the second lecture of LTE throughput, and in this lecture we are going to study SNR, CQI, MCS, means how these factors affect the LTE throughput. This we will see, and before studying it, let's go through what we studied in last lecture. We studied about duplexing technique and modulation techniques in detail. Okay, so we studied that for in QPSK 2 bits per symbol can be transmitted. For details of symbols, how these bits are transmitted in symbol, kindly refer my lecture number 1. Okay, and in 16 QAM 4 bits per symbol can be transmitted, and in 64 QAM 6 bits per symbol can be transmitted. Okay, before moving ahead, I would like to tell you one more thing, that is code rate. There is a term code rate. Okay, so suppose this is our modulation scheme and code rate which we are using is 0.5. so in that case, instead of 2 bits per symbol, only 1 bit per symbol can be transmitted. 1 bit per symbol. Okay, similarly, if if code rate is 1, in that case all 4 bits can be transmitted per symbol. The situation will remain same. Okay, 4 bits per symbol. And again, if here code rate used is 0.5, then instead of 6, only 3 bits can be transmitted. Means half of the bit cannot be transmitted if code rate is 0.5. So what happened to those half bits? Means 3 bits, these 3 bits are carrying data. Okay, so other 3 bits will be added as a redundant bit, or you can say parity bit, which is used for error correction. Fine. Okay, so along with good modulation, your code rate also plays an important role in throughput, because you can see here we can use 64 QAM but code rate is 0.5. that's why only 3 bits are able to carry data, whereas in this case 64 QAM we can transmit data on 4 bits per symbol because our code rate is 1. Okay, and similarly here also one bit is used to carry data, the other bit is used for the other bit will be for redundant bit. Okay, and here 0 redundant bits are present. And let me tell you a little bit more about redundant bit. What happens generally, suppose this is my E node B, okay, and this is my UE1 which is very far away from E node B, and this is my UE2 which is quite closer to E node B. So UE1 is in poor coverage, right? It is in poor coverage. Okay, so due to poor coverage, what UE1 will tell E node B to use QPSK. Okay, why QPSK? Because QPSK is a robust technique, and bits which are carrying data will be less. Okay, and so there will be probability of error will be less in case of QPSK, whereas the one which is closer to this E node B, it will, or let's say UE2 is it's in mid of some coverage of E node B, and UE3 is quite closer to E node B. So UE2 will ask E node B to use 16 QAM, and UE3 will ask E node B to use 64 QAM. because with UE3 probability of error will be less. Okay, so all the bits can be used to carry data. Okay, and here the probability of error is average, that's why it is asking eNote B to use 16 QAM. Okay, so this is a general thing that I have explained. Let's move ahead. Okay guys, so let's say this is my eNote B and this is my UE. Okay, so the signals from eNote B is coming towards UE, and UE, what UE will do, UE will decode the reference signal. Okay, and it will find out RSRP, you can say. Basically UE is finding the how much coverage or signal strength it is getting. Okay, so after decoding a reference signal, what UE will do, UE will send some details to eNote B. These are signaling details or control plane, you can say. So the first one will be, you can say, it will be your CQI. So CQI tells about the radio quality, means what kind of RSRP or the strength of signal UE is receiving. On the basis of that, UE will send the value of CQI to eNote B. Value of CQI varies from 0 to 15. 0 is in use, so you can say it's from 1 to 15. Okay, so there is a table defined in LTE spec. Let me show you that table. Just a second. This is the table I am talking about. So suppose UE means if UE is getting good coverage, then UE will report high CQI value, that is 15, and if it is getting bad coverage or poor coverage, then it will report CQI 1. Okay, so suppose our UE is in good coverage, so UE will report CQI 15. Okay, so let me write it here that CQI reported will be 15 because UE is getting very good signal strength from eNote B. Okay, so what this table says, with CQI of 15, eNote B can use 64 QAM. Okay, that is 6 bits per symbol can be transmitted. Okay, but you can say the code rate, that is this column, that is code rate. Okay, so the code rate with CQI 15 is to be used with 0.9. okay, and 0.9 means it's approximately 1. Okay, so that is why you can see that bits per resource element or symbol, they are remain 6, because with 64 QAM 6 bits per symbol we can transmit, and if code rate is 1, so approximately the full bits can be transmitted. Okay, similarly, let me give you another example. Suppose I am using UE has reported CQI 11. Okay, so with this eNote B can use QAM technique, modulation technique as 64 QAM, and code rate will be of 0.5. Okay, so with 64 QAM 6 bits per symbol can be transmitted, but as we can see here code rate is 0.5, so that is why half of the bits will be used as redundant bit, and half of the bits, that is 3, will be used to carry the user data. So in our case, let's say 15 CQI is reported and almost full bits can be transmitted, or means you can say full bits per symbol can carry user data. Okay, so let's come here. So CQI 15, with CQI 15 we have seen code rate is approximately 1, so bits per symbol will be your 6 bits per symbol. Okay, one more thing, with these parameters, UE is telling what kind of means UE is telling to eNote B what kind of radio quality is there in downlink direction. Okay, so and UE is saying, you can say UE is saying to E node B that if you provide me these things, means code rate 1 and 64 QAM is also there. Let me write that as well. 64 QAM, that is with CQI 15, code rate 1, 64 QAM. The bit error rate will be less than BER, that we call BER will be less than or equal to 10%, because in spec it is mentioned that your bit error rate should be less than or equal to 10%. So this is the belief of UE, that with this kind of configuration or parameters, the bit error rate will be less than 10%. Okay, so E node B has received the CQI value from UE. Okay, and so on the basis of CQI value, it will find out the MCS, that is modulation coding scheme, to be assigned to UE. I'll show you a table, just a second. See, this is a table. So here CQI are mentioned, okay, from 1 to 15, and these are the modulation techniques, okay, and these are the code rate. Means actually this table, means CQI and MCS mapping, is vendor specific table. It's not written in spec anywhere. Okay, so every vendor, means Samsung will have its own table, and other vendors, Ericsson, Nokia, will have their own table. So on the basis of this, let's, in our case CQI 15 is used. Okay, so MCS used here is 28. Let's, we are working in working with Ericsson network. So in that case, if CQI 15 is reported by UE, then MCS allocated by network or E node B will be 28. Okay, so let's get, go back to our description. So CQI 15 is reported by UE. So we have seen on the basis of, means the vendor specific table is there, which map do these two parameters. If CQI 15 is there, then allocated MCS will be 28. Okay, and this thing is vendor specific, not written, this table is not written anywhere in spec. Okay, so we got the MCS. So there is another table in spec. Okay, so this is the table I am talking about. Okay, so this is, so in our case, if we talk about our case, MCS allocated is 28. Okay, so in that case, modulation order is 6, means we have seen that 64 mm, 6 bits per symbol can be transmitted, and this index, transport block size index, will be 26. Okay, so this is also a table that we have to use. So after getting CQI, MCS is determined, and after getting MCS, there is transport block size index. So we have seen this value as 26. Okay, that is for 28. Why 28? Because CQI was 15, so MCS was 28, and the TBS index is 26. So this we have find out. Now there is another table. Lots of tables are there, but this one is the last table. Okay, this is the table which maps the transport block size index with number of PRB. Okay, so if transport block size is 26, as we have seen this thing already, that for MCS 28, transport block size index will be 26, and for transport block size 26, if a UE is getting the 100 PRBs, means suppose in our network only one UE is there, in that case all the PRBs, if you are using 20 megahertz bandwidth which has 100 PRBs, then all those 100 PRBs will be allocated to that UE. In that case you can transmit this amount of bits, and remember this is bits per subframe. All these values are bits per subframe. So 75376 bits can be transmitted per subframe. Okay, let me write these things here as well. So transport block size index 6. Okay, and suppose only one UE is present. In that case all the PRB, that is 100 PRBs, will be allocated to my UE. Okay, so as we have seen, for transport block size 26 and NPRB 100, bits which can be transmitted per subframe are 75376. Fine. Okay, and in similar way, suppose two UEs are there. Okay, in that case 50 PRBs will be allocated to one UE and 50 other PRBs will be allocated to other UE. In that case, actually, if you read a spec, this is a very long table, means it starts from 1 to 9 till 100. Okay, so in that case again we will map these things, means let's say for example a UE get this number of PRB allocated to UE are 94 and transport block size is 26. In that case I cannot see here, let's say transport block size is 25 and number of PRB is 94. In that case this amount of bits per subframe can be transmitted. Okay, so this is the maximum. This means these are the ideal condition, you can say, means everything is fine, means only one UE is present, bandwidth is maximum 20 megahertz, and all PRBs are allocated to a UE. Okay, and 64 QAM is also used. So means ideal situation we are considering here. Okay, and guys, you see that we are talking about this transport block size index. Okay, let me tell you what transport block size is. Actually, if you check the layers, so it's like PDCP, RLC, MAC, and then your file layer. Okay, so whatever the MAC layer transmit to file layer, it sends its bits in transport block, and this file layer will then forwards your data over the air in terms of subframe. Okay, and we know subframe are of 1 millisecond. Okay, so this bit, these are the bits per subframe. Let me write this thing, bits per subframe. Okay, so this amount of bit can be transmitted in one subframe. Okay, so what we can say here, that in 1 millisecond we know that subframe is of 1 millisecond. Okay, so in 1 millisecond 75376 bits can be transmitted, right? And in 1 second this value will be 75376 1000 bits can be transmitted. If we convert into MB, so it will come around like this, 75.37 megabits. Okay, in 1 second. So our throughput will be 75.3 Mbps. Okay, so guys, this is the downlink throughput, right? And when in last lecture we calculated the theoretical value of throughput, it was come around 100 Mbps, and I said the resource elements or symbols, you can say, here symbols are there, right? So where the bits will be transmitted, as I told you in last lecture. So in theoretical calculation, all these, actually one subframe will have around 168 symbols, right? So in theoretical calculation, all 168 symbols were carrying the some bits, but in actual case some bits are used for signaling also, like for reference signal and for your PSS SSS signal, okay, and some are used to carry the PDCCH, PCFH, PHICH. Means lots of signaling are also means some signal symbols are occupied by signaling data also. So in that case, throughput will be degraded, and this will come around this value, 75 Mbps. So this value is calculated after considering all the signaling parameters, okay. And if you use 2x2 MIMO here, so in that case your throughput will be 75 multiplied by 2, that is 150 Mbps. Okay guys, so that's all for CQI and MCS and SNR. I hope you like my video. Okay, thank you.